Hi, everyone. Thank you for joining us today. I think we will have a few minutes before everyone is attending here, but I wanted to say a warm welcome to all of you. And this is the first of the GX webinars in a series. There will be four more over the next few weeks. Personally, I'm looking forward to the Python plugin and scripting one we have in 2 weeks, but you can all look on our website and see the different topics and sign up for the next webinars if you like. Today we will have Christian present for us. He's a very established geotechnic engineer and the driving force behind Optum GX. So it will be fun to hear his introduction of GX to you, and I will send the recording to everyone tomorrow afterwards, so you can re-see if there's anything you want to revisit after this webinar. And you can, of course, ask questions in the chat. So thank you again for joining, and I will hand over the word for Christian.
Thank you, Isabella. Yes. You can all hear me? I'm good. Going. Okay, great. As Isabella said, this is the first in a series of webinars that we will be having every Thursday at this time for the next 4-5 weeks until Christmas, more or less. And this first one here is just a basic introduction to GX. What is it all about? How does it differ from our other programs, G2 and G3? What are some of the capabilities and so on? So sort of a more general introduction. It's a very large program, so there won't be time to go into every single detail of it, but I hope I can give you sort of an overview of how it works and what the program is capable of. So just a very brief introduction to Optum Computational Engineering. We were founded in 2013, so we've been around quite a while. Our core business is software development and we like to sell some licenses as well. We also do a little bit of consulting, often using our own programs. And then we have done recently also quite a bit of specialized development of apps, or what we call plugins to GX. So it's small apps that use Optum GX, but otherwise are kind of standalone. I'll say a little bit more about this as well. Complex constitutive models, if someone has some very specialized needs, and various other things. We have undertaken these specialized developments. Our main programs, so we are both in geotechnics and in concrete. Today it's about geotechnics, where we have two programs, Optum G2 and G3, for 2D and 3D respectively, and then our new program GX, where X stands for either 2 or 3 or both of them, you could say. So Optum G2 for 2D geotechnical finite element analysis, and G3 for 3D. So you have these two programs, and if you mix them together, well, then you get GX, and that is what GX is. It's a program that's been development, you could say, been developed from scratch, but it has the combined functionality of G2 and G3 plus actually a lot more. So it's 2D and 3D in the same package. And I will just switch to the program so you can see how it actually looks. So this is the beast, where for those of you who know G2 and G3, you will see some differences, but also I hope some similarities. We have what we call the canvas here, where we can define geometry and apply materials and so on. So the first thing you want to do, of course, is geometry. And then in G2 and G3, the materials and what we call the features, the loads and supports and so on are up here in the ribbon. This ribbon here is now dedicated actually to geometry manipulation, so definition of geometry and copy and move and so on. The materials are over here in this tab, and you can drag and drop those as in G2. So MC basic, a basic more Coulomb material, and I've sort of drawn a foundation here, so that would typically be assigned a rigid material. And then features, well, we have the same features, the same and more than in G2 as in G2 and G3. So standard fixities is something we'd want to do, and then we might want to apply a multiplier load on the top of the foundation here. And for those of you who are familiar with G2 and G3, know that a multiplier load is a load that you are looking for, you're looking to multiply, basically, find the number that you should multiply into this load. It has a value of 1 or -1, so 1 downwards, 1 kPa downwards. You want to find the number that you should multiply onto this value in order to be at a state of collapse. And that analysis type in G2 and G3 is called limit analysis. Now it's called load multiplier. So we've changed the names of these analysis types, but it is the same as we had before. So they're slightly sort of more referred to what is actually done rather than in G2 and G3, they were somewhat technical. And then you press play and you get a result, a load multiplier of 277.7 and a collapse mechanism that looks like this. This is for a material with C and Phi 5 and 25 respectively, and a unit weight of 18. So from that point of view, everything is the same as in G2. Things are organized a little bit differently, but the analysis capabilities are the same and then a little bit more. What is really different from the two programs is that we have here a 2D world, 2D canvas, and we have also actually a 3D world. So in the same program, you can switch between 2D and 3D. I'll talk a lot more about that today as well. That's quite useful in many ways. So if I was to do something similar, maybe sort of use symmetry and draw a foundation like that, and then the same materials. And a rigid there, and then some load on top. Again, a multiplier surface load, and then standard fixities, and I'm basically ready to do the same thing in 3D. And the result is like that. The value is well, it's a little bit different from 2D. The width of the foundation I've just sort of drawn by freehand is also a little bit different. So, but sort of in the same neighborhood, and a collapse mechanism that kind of also looks similar. So that's how the program looks. And also another major difference from between G2, G3, and GX is this so-called model outline over here that we don't have at all in the other programs. And this turns out to be really quite useful. You can do without it, because we do without it in G2 and G3, but in many cases it is quite useful, basically for inspecting. You can inspect the geometry exactly, especially in 3D, it can be quite useful to have this list of the geometric object, the solids, the faces, and so on. I'll also give some examples of where that is actually very useful. So that's how it looks. And if I just go back to my slides, that wasn't my, then the agenda for today, I would like to say something about G2 and G3 versus GX as we go along. I've already said a little bit capabilities of GX, 2D versus 3D in GX, because often the way things are at the moment, and the way we, in a way, thought of it as well, is that you have a separate 2D program. You have a 2D program that you, of course, develop first, and then once that's up and running, then you develop a 3D program. And those are two separate programs. To some extent, maybe they can communicate with each other, but only to some extent. Having 2D and 3D in the same package is more than just having two separate programs in the same package. There's a kind of an interplay between 2D and 3D that is made possible by having 2D and 3D in the same package. So you can extrude 2D geometry into 3D. You can take sections of 3D geometry and treat it in 2D. That's really quite useful. Examples of that as well. Python scripting. Isabella mentioned we have in 2 weeks a dedicated webinar on basically how to take control of the application of the program via Python scripting, by commands issued in Python. That's also extremely useful. And some examples as we go along. So the whole basic motivation for all our programs is to develop software that allows engineers to focus on engineering. I should say, I know we have a lot of academic users as well, so we would also like those people to be able to focus on the questions that they're interested in, and not a whole lot of time tweaking algorithmic parameters and to get things to run as they should. And how do we achieve that? Well, well-designed user interface and with a sort of a logical workflow is important. But what is really, in many ways, much more important is the computational technology. So we talk about OBFEM, optimization-based finite element method. That's sort of what we like to call the version of the finite element method that we use, which is the same as the conventional one in the sense that it gives the same results, but the equations, you could say, are solved in a very different way, which allows us to have some dedicated analysis types for dedicated tasks. So, for example, what is the bearing capacity of a foundation? It's a very direct question, and that's traditionally answered in a very indirect way, namely by setting up a problem like this, something similar to what I just showed. Then you have, then you typically you generate a mesh, and then what you do is you start increasing the load here on top of the foundation and monitor the settlements as you go along, and you get this famous load settlement curve, which sort of should look something like that. But and then you read off the bearing capacity. At some stage, you assess, okay, the settlements are so large that now we can say it's failed, and that load is then the bearing capacity. So it's a kind of an indirect way. Of course, it works when it works, that is, because often you see that it works quite nicely when you're not that far away from failure. And then when you get closer to failure, you can get something like this, where you wonder, what is it really going on here? Is this a physical thing, or is it kind of a program that's acting up a little bit? And usually it's the latter. And then the question is, of course, what is the bearing capacity here? Maybe it's a little bit exaggerated, but I think you get the idea. And even if you do get a nice smooth curve, there's still the question of how is the result, the bearing capacity in this case, affected by the mesh, so say the number of elements. And typically you have to do a mesh convergence analysis. You start with 1,000 elements, record the results, then 2,000, 4,000, and so on, until the sort of the bearing capacity, you could say, converges. So a direct answer to a very direct question is not really that straightforward. And so what we instead have focused on is answering these direct questions by having dedicated, we call them analysis types. So the load multiplier that I just showed you is one analysis type. We have one for factor of safety analysis. We have one for deformation analysis. Load deformation, that's where you have sort of a step-by-step increase of the load. C-pitch as well. steady state, and that's a new feature of GX as well, transient seepage, and then also initial stress. We have a dedicated analysis type to determine initial stresses on the basis of the earth pressure coefficient. And so I'll actually switch to the program again, and the problem I solved here was I have, it's a problem that was like this, and a more Coulomb material. So, and I will use a cohesion of 0 and a friction angle of 30 degrees, a unit weight of 18. And for the foundation, just a rigid, weightless material. And then apply a multiplier surface load, and then standard fixities. And this is, now I'm up and running, and I would like to determine the bearing capacity. And the way to do that is via a load multiplier analysis. You will then see some settings attached to this model. The first setting here is the element type. So there's different element types. There's the mixed, that's sort of the default element. But there's also something called lower and upper, and then Gauss, which is just a sort of a more conventional 6-node finite element. But the idea with the lower and upper is that they determine, they calculate basically rigorous upper and lower bounds on the collapse load. So if we start with a lower bound, well, we get a lower bound of 596. And then we could have another model where we do an upper bound, and that would then be quite a bit more, 1119. So we know that the true solution is somewhere in between. We don't know exactly where in between. If we use more elements in the lower bound, the lower bound will come up, and in the upper bound, that will come down. So for example, if we switch to a medium mesh instead, we will have something that looks like this. So the lower bound, I'm not sure that actually came up, but it's more or less the same. The upper bound came down a little bit. So in that way, if you're happy enough with this capacity, the lower bound capacity, then you're sort of done. Then there's no need to know really what is the exact solution. If this is enough, it's enough. And then we have also the idea with this mixed element is it's an element type that sort of combines features of the upper and lower bound elements to provide what is usually a very, very good solution. And that's why it's the default element. So 800, which is somewhere in between, what did I have, about 600 and about 1000. So 800 is more or less right in between. So that's one way of basically doing things. And if we look at the collapse mechanism, well, that looks like this. And to get a more accurate solution, well, what you can do is you can either increase the number of elements, or you can use what we call mesh adaptivity. So if we just go to the upper bound here, 1035 was the capacity, and I have a collapse mechanism that looks like this. If we look at the strains instead, epsilon 1 minus epsilon 3, that looks something like this, and you can see sort of the slip lines. I should probably have made this soil domain a bit wider, but the idea with mesh adaptivity is then to basically adapt the mesh here where things are happening, and then use coarser elements, larger elements out here where not much is going on. And you say yes to that, and then it runs through some iterations. So you start basically with a uniform mesh. You find what I had before. Yeah, that was 1119. and then you adapt the mesh once, down to 941, and once more you are at 887. You can see the mesh has been adapted better to basically capture these slip lines. I think there's somewhat of a rotation here, which of course is completely legitimate, and which is also how you typically see these foundations fail in real life. They don't move straight down. They sooner or later rotate, and even though this is a symmetric problem, the mesh is in this case unsymmetric. Will always be slightly unsymmetric, so that's what generates this rotation. Um, oh, um, oh, so I did the result. I did the analysis here. So the ones I've just shown you for a coarse mesh, quite a bit of a difference between the upper and lower bounds. You can take the average of the upper and lower bounds. That's usually a very good estimate of the true solution. And then you're at a certain distance, you could say, from each of the two. So you can actually already see what the maximum error is. So we can say the exact solution is 857 plus minus 30%. It could be 30% higher, it could be 30% lower. But as you increase the number of elements, and also as you use adaptivity already, it's from 30 down to 13. And then as you increase the number of elements, it goes steadily down to something like, well, this is what I call an ultrafine mesh with adaptivity 1%. Plus minus, which of course for practical purposes is more than enough. But what is also worth noting is the performance of the mixed element. So if the exact solution is about 810, well, the mixed element, even for the coarsest mesh, is pretty spot on, as a very small error. So this is a really good element, which is available in G3 for 3D, but not in G2 for 2D. Now it's available in both 2D and 3D. So accurate finite elements is also a way of, it's also part of, you could say, what you could call user friendliness, and as is mesh adaptivity. So I know this was an academic example, but mesh adaptivity is also actually very useful for more realistic problems. This is a problem that was sent through by a client some time ago, and you can see it's sort of it's not a very complex problem, but it has all these nasty layers here, which makes it kind of difficult to get a proper mesh unless you use a huge number of elements. You have to mesh all these thin layers, and eventually, if you just use a standard, more or less uniform mesh, well, you can see it doesn't really capture the failure very well. It looks like something like this, and you would really want more elements up here. But if you only have a uniform meshing at your disposal, well, you'll have a huge number of elements everywhere where you don't need them. And mesh adaptivity is then really quite useful for problems like this. So applications, of course, Optum, both G2 and G3, and definitely GX, is a lot more than bearing capacity and failure. It's a general finite element program. We have also some really quite nice tools for deformation analysis and some advanced soil models and so on. So the applications is really all the applications, all the geotechnical applications you can think of. Foundations, slope stability, retaining walls, excavations, embankment construction, and so on and so on. Piles, of course, that's often kind of would be handled in 3D. Materials, as I said, yeah, well, it's from the basic, more Coulomb, Tresca, to the more complex hardening soil, modified cam clay. That's you could call it modified cam clay because it's quite a modified and extended version of cam clay. It's quite similar to what is known in some circles as the soft soil creep model. Creep is also included here. So I think we have a good selection of models from the simple, which is sometimes preferred, to the more complex. Structural elements, of course, as well. Again, the same as in G2, and then extended to 3D. And that's not necessarily always completely trivial. You can think of a sheet pile wall. In 2D, it's sort of modeled as a kind of a beam element. In 3D, it's of course not really just a flat plate element. It's an element that has very different properties about two axes. The weak axis, where basically you have very little strength and stiffness, and then the strong axis, which is usually what governs things. Geogrids, pile rows, nail rows, both in 2D and 3D, and then beams, actual 3D beams for use in 3D. So I wanted to just show an example of an excavation, because just to it's quite a common application, and just to show that it is about a lot more than failure. So it's again a very simple problem, and I've already solved it here, but it's very easy to set up. You draw this box, you apply the material. This is sort of a sand material, C equal to 0 and 30 degrees friction. Then apply a plate element. In this case, it's a very simple plate element with an EA and an EI and a yield moment, a yield force, which is not really relevant. We have interfaces come with the plate element. So when you apply a plate element, it comes with interfaces that you then have to, you can set the reduction factor. Yeah, it's just set to 1, so no reduction at the interface. Some people would say that 2/3 is the way to go. It sort of depends. And then you have a number of stages where you progressively modify things to basically simulate the excavation. So the initial stress stage, and then a deformation stage or deformation model linked to the initial stress one. You can see this small sort of link between the two models, where you then excavate some material. And you go further down and you excavate some more and also insert an anchor. And then a final excavation stage here. And then I finish off with actually a factor of safety analysis. That's maybe where you most often would want to start, actually. So if we start with that, we can see the collapse mechanism there, and it's 1.33, so that's probably okay. And then the excavation stages where you have actual deformations in millimeters. The factor of safety analysis, of course, just gives you the collapse mechanism, but as you go down, you get actual deformations of the wall and the soil. So this is the last excavation stage, and if we just plot the plate displacements, so about 9 millimeters of displacement of this wall at the at the final stage. Now, one of the things that's been criticized with this way of doing things, or well, if we just start with the positives, I quite like this way of doing things, because you have a sequence of models that are completely independent. And I think it's a sort of a quite intuitive way of thinking of an excavation. It is removal of material and then insertion maybe of anchors and so on. But the problem with this is that if you decide at the end of the excavation, or at some stage during the process here, that you would want to make the wall say 1 meter deeper. Well, since these models are all independent, you will have to go into every single model and make that modification. And with 4 models here, that's not so big a job. If you have 20 models and you have to do it, I don't know, 10 or 20 times, then at the end of the day, you become a little bit tired of that. So as an alternative to this way of doing it, which is the G2 and G3 way of doing it, we've introduced a new concept with stages. And to show you how that works is I'll actually clone this model here, so create a copy of that. So forget about all these, and let's get that one back to where it was there. And so the idea is that you have a model that has all the geometry, has all the soil layers, you could say, predefined. I just see what I did here. Has everything you want to do during this excavation kind of predefined like this, and standard fixities. So this is a model, this kind of a parent model, and then under the model we have what we call stages. And in the stages, you can then, the idea is you can then switch on and off things. So in the initial stress stage, I don't want the anchor here. So I go over here and turn that off. That's where the outline really is handy, is for turning things on and off. And I go down. Oh, I should have created a new stage. That's then by default a deformation stage. That's what you usually want. And in this case, it's this guy here I want to switch off. And down further, I can also do it by right-click, deactivate that, and then I want to, at the same time, activate the connector. And for the grout here, I use a nail row. And then the final stage where I deactivate this one. So it's the same thing as before, but the advantage is that I can only change the geometry in the model. So if I want to make the wall 1 meter deeper, I do it once and for all in one place in the model, and then that change is carried over to all the stages. So I think that is quite convenient, and definitely if you have a lot of stages where you anticipate maybe also a lot of iterations back and forth with various things, it could be other things than this, then I think this is a pretty good way of doing it. If we just run it, we get the same result, of course, as before. So that was with about 9 millimeters of deformation of the wall. So it's a different way of doing the same thing that is now available. So we know from having 2 programs, G2 and G3, a 2D program and a 3D program, that the vast majority of users work in 2D. And from time to time, we get the question, what is the purpose of 3D? Because we are absolutely fine with 2D. And I think that's to a large extent true. And also, if you look at it historically, geotechnical engineering is one of those funny fields that have been developed actually with more or less specific reference to 2D plane strain, because many structures are approximated very well in that way. And so we, in many ways, are fine with 2D foundations. If we want to go into 3D, we have shape factors, slopes. They're usually sort of long structures, retaining walls, same kind of thing, where 2D is quite all right. On the other hand, the world is 3D, and more importantly, when you have something that is not exactly 2D, you can make approximations, but that is often not very simple to do. It's often very complex. It often takes a lot of time, and you are left in most cases with 2D models that you don't really believe in. Sometimes you can convince yourself they're conservative, but sometimes you quite often you kind of suspect the opposite. So in those cases, I think it's useful to go into 3D, especially if 3D, as it is in GX, is right at your fingertips. Of course, if you have to buy and install a new program and get to learn that and so on, then it may be a different story. So that was one of the ideas of GX. I think it's mostly, and I think it is going to be mostly used, that the 2D functionality is still what most people are going to use most of the time, but in certain cases, it is justified to go into 3D. So I've sort of identified, you could say, four types of problems. There are the problems that are 2D, and they're the most common. So a long wall like this, a secant pile wall, that would not be reasonable to approach to attack this wall in 3D. You would want to take out some sort of a section, critical section, or maybe a couple of them, and then analyze those sections in 2D. Then there are 3D problems, that genuine 3D problems where you cannot really approximate things in 2D. For example, this is actually a monopile, so we've done quite a bit of work on those types of structures for offshore wind turbines. So lateral loading of a monopile like that, you have to go into 3D. You can't do that reliably in 2D. And there's the problem down here, which is this was sent to us by a G2 user who asked us, can you please help us make an approximation of this as a 2D problem? And I think that can maybe be done, but this is also a problem where you would think it's not that complex, so just solve it as an actual 3D problem. And then there are a sort of an interesting class of problems that we sometimes call 2.5D problems. So that's problems that are mostly 2D, but have some, in reality, quite annoying feature which sort of renders them actually 3D. So for example, a long slope reinforced with discrete piles. It's mostly 2D, but because of these discrete piles, it does become a 3D problem. Well, I'm just going to jump a little bit in my slides and sort of show that. So that's this problem here, and so the story is as follows. We have a slope here, C equals to 5 kPa, phi is equal to 25, and we find a factor of safety of 1.08. And if we think that's not quite enough, well, then you can introduce these piles as reinforcement. And if you sort of just model that in 2D, well, you get result that looks like this. So a factor of safety of 1.29. So that's quite an improvement, and the failure mechanism is also, of course, very different. But of course, what you're actually doing here is not a sequence of discrete piles. What you're actually modeling here is a long slope with a long wall cutting through it. And that's not what you want. What you want is more something like this. You want sort of a sequence of discrete piles. And for that, to do that properly anyway, you have to go into 3D. It's not really a very difficult 3D problem, because by symmetry, you can convince yourself that you only have to really model half a pile and half a gap. So there's lots of symmetry planes all along here. So what you have to do is just half a pile and half a gap. But nevertheless, that is a 3D problem. And if you solve that 3D problem, well, you get actually, in this case, a factor of safety of 1.28 compared to the 2D one of 1.29. and you see the failure mechanism is also quite different, quite similar. It's mostly down here. Yes, we do have a bit of flow in the gaps, but not very much. So the 2D model is kind of validated. You'd be able to continue working with this 2D model. Of course, you don't know that before you have actually done the 3D analysis. Just to show you how that's done, and this is sort of where the interplay between 2D and 3D comes in. I have it here. So that's this problem here with well, the 2D version of it, where we found then a factor of safety. Let me just run it. 1.2, well, 1.29, yes, it was, and a collapse mechanism that looks like this. Now, what I want to be doing actually is I want to extrude. I want to basically, so this is seen from the top, and this line here is a symmetry line, a symmetry plane. This here is a symmetry plane. So if I say the yellow dashed line here is my center plane, then what I want to be doing is extrude the soil 1.5 meter into the plane and 0.5 meters out. And the pile, I want to extrude that 0.5 meters out and nothing in. And we have settings that allow for exactly that. And it's over here, it's called 2D to 3D. So depth in 1.5 meters into the plane and 0.5 meters out. And then the pile 0 in and 0.5 out. And then I press this extrude button up here, and this is then what I get. And you can see there's a gap here between or behind the pile. I've not set up anything about what I want there, but this gap is very easy to fill. I just need to draw a line here, and then this is recognized as a closed surface. Same with this one and the ones behind. And if I have a collection of closed surfaces that define a volume, well, then I have a volume, and I can apply the material there and standard fixities, and I'm basically up and running. And yeah, now this is, I think, probably quite a coarse mesh, so I don't think I'm going to get the exact same result as I showed in the slide, but let's see. Yeah, it's going to be, I think I had 1.2, 1.28, 1.34 here, so a few more elements here would have been good, but let's just have a look at the collapse mechanism, and you can see that is qualitatively similar to basically the 2D collapse mechanism. A little bit of flow in the gap, but not very much. So the 2D model is validated here, you could say, and as I said, you can continue with that. But there are cases as well where you would go quite wrong continuing with the 2D model if you have a clay layer up here, so no friction. You can play the same game point, factor of safety 0.68, so that's not even stable. You introduce a pile or a row of piles, treat it as a 2D wall, and you get a very good factor of safety. But if you actually go to 3D and solve this problem, well, things don't look so good. So it's to do with the arching effect, of course, but it just the point is you need to be somewhat careful with these 2D approximations, and you have now a tool where they can be checked. So that is that. Then there is the you could say the opposite problem, where you have a sort of a fairly complex 3D structure, And I have that here as well. Let me just open that. This is a so-called a rock berm. So this blue part here is the seabed, and then the gray mass up here is rock that's been dumped on the seabed. Basically, it's to support a pipeline that comes here that spans this kind of little valley. And this is very, very soft clay, under shear strengths of a couple of kPa at the top, and then I can show you here, and then increasing somewhat as you go, increasing with depth, but very soft sediments, and then you have this massive rock on top that, of course, needs to be stable. So if you run a factor of safety analysis on this, you find a factor of safety, it's just stable 1.04 or 1.05 if you like, and it fails like something like this. You can't see that here, but you can take a cut through like this, and then you can turn off the mesh, and maybe this one as well, and then you can see it actually goes down into the seabed. It fails through the rock berm here, but of course also or goes down and fails in the soft sediment as well. Now the question is, can you trust a result like this? And one way of kind of reassuring you that it's not completely wrong is to take a 2D section through this, could say sort of let's say a critical section. So something like from here to here. I've put some markers out here. So take a 2D section from there to there, and then you have that 2D section, and you can then run a factor of safety analysis on that. And in this case, 0.8. It was always expected to be less, of course, because 2D is conservative. There's much more mass effectively failing in 2D than in the actual 3D problem, but the same kind of failure mechanism, and factors of safety that are different, but not really worlds apart. So that's another, I think, nice application where you go from 3D to 2D rather than the other way around. And as you can hopefully see, it sort of happens quite seamlessly. Modeling in 3D as well is something I'd like to just say a few words about. It's something you have to experience yourself, I think, to kind of appreciate, but it's really quite simple. Most 3D programs use some third-party library, Open Cascade often, for open or some third-party solid modeling library, which there's a lot of good things to be said about them. We use that in G3 as well. But at the end of the day, you find that you get messages that the model has broken and there's no real way to fix it. So what we have done here with the GX development is we've actually developed our own 3D solid modeling engine from scratch, where we have full control over all the operations, and where we really have a lot of flexibility, a lot more flexibility than you would have in with the sort of the third-party libraries. So if you want to have sort of a pyramid like that, you can have it have a solid like that. So the idea was to make 3D modeling as close to 2D as possible. And I think we've achieved that. 3D will always be more complex than 2D, but I think this is really, really very useful. This solid modeling engine we've developed for this program. But as I said, it's something that I think you have to convince yourselves of. So I hope that will happen. Yeah, and So what we really set out to achieve, I think, is 2D is something that is very widely used. It's something that's used by everyone. 3D is still something that is quite painful to use. And so we wanted to take at least one step closer to 3D being just a tool you use on a routine basis. And I think we've taken quite a step in that direction. There'll of course still be the computational times are longer, and the modeling is also more difficult. But I think it's as easy as it gets. It's as close to 2D as you get with this modeling tool here. Good. So yeah, so 3D involves a lot of challenges that don't exist in 2D. Modeling is one, the geometry, but also the computations. And Optum GX is a program that has taken these challenges seriously, and the result is 2D and 3D in the same package. Close integration of 2D and 3D. So there's the extrusion and then the 2D cuts through 3D models. So we've achieved something that is as close as the same as 2D, just 3D as possible, I think. And it's something that facilitates routine use of 3D analysis in geotechnical practice. Other improvement, so we have faster algorithms. The equation solving, if you like, that drives the whole thing is faster, and also the algorithms, the number of iterations for something like factor of safety analysis has been reduced. More accurate the mixed element, better mesh adaptivity in 3D, some new models. The hardening soil small strain model is available, and we call it modified cam clay, but it has the same functionality as soft soil creep. More user-friendly handling of interfaces than in G2, and more structural elements. For example, these sheet piles in 3D, I'll introduce those in, I think maybe it's even next week. We have another webinar on retaining walls. Transient seepage and a new analysis manager, as I showed, and also rather better reporting tools than in G2. So then the very last thing I just wanted to say a few words about was Python scripting. So what can be done is that you can take full control of the program via Python. And we have actually an inbuilt Python, it's called an IDE, Integrated Development Environment. It sounds more complex than it is, but it's basically a Python editor. And then you have the Python command prompt running over here. So you have Python up and running. You can say 1 + 1 is 2. And then in this script that you can also run, you have a number, you have various commands that that all do something. Now this is not exactly the script I had expected to see. I had expected to see a simpler script, but let's try to run that. That's not going to run. Was the getting started script, where you can see we have commands like add rectangle. That's the scripting analog to the rectangle tool. So rectangle, first point, second point. Same here in the script, first point, second point, and another rectangle. And you can select objects and then assign, for example, a solid, that's a solid material. and loads, and you can set analysis properties and so on and so on. And so if I run this script, just move it over here, something should happen on the screen. What happens on the screen is that this problem here is set up and run. And then the results can also be a result. I just extract the load multiplier, so that's this number down here. But all the results, the stresses, the displacements, etc., are available. So it's actually also very good for post-processing of results. We have, of course, the results available here in the UI, but quite often you would, that's our experience, people request all kinds of results that are either not available or not so easy to make available. Via Python here, you have direct access to the calculation engine, so everything is available there. That's in 2 weeks. I will go through some of the possibilities of scripting, and one of the really interesting possibilities is the possibility to do to basically develop what we call plugins. So that's small programs, small Python scripts with a little bit of a user interface attached to them that plugs into to GX. So I'll go through the details of how to get it into GX as well. So here is you can say an app for basically sheet pile walls. So instead of modeling it by mouse click, well, you model it by specifying the ground level, the excavation level, and so on. We have soil layers. You can have more than one soil layer, and you can have more than one anchor as well. And once you're ready, you can then generate the geometry like that. Or alternatively, there's also an analysis type for basically determining the tip level so that you get a factor of safety equal to 1. So here we just run through the whole thing a number of times. So iteratively determine the tip level until we get a factor of safety equal to or close to 1. So this is a great way of automating things, both setting up problems and actually also running problems. And then based on the result you get in one, you could say iteration, modifying the problem and continuing onwards. But that's in 2 weeks. And I think that's it. And I think I went a little bit over time, but my apologies for that. But thank you for your attention. And we will